Hello students, welcome to lecture of Kinematics and Theory of Machine, and we are going to start new chapter today, which is a brake. So before starting this chapter, you must learn the chapter friction, because in brake there are lots of fundamentals are there which is totally depend upon the frictions. Okay, so first you learn the friction and then you can start brake. And so first check this. Brake is a device by means of which artificial frictional resistance is applied to a moving machine member in order to retard or stop the motion of machine. As you know that we use the brake in a lots of machinery and a vehicle to stop the rotary motion or decrease the rotary motion of that particular element. Okay, and second element you also know that, which is the clutch. What is the difference between brake and clutch? Major functional difference between clutch and the brake is that clutch is used to keep the driving and driven member moving together, because clutch allowed to move the driving and driven independently, and it can when we require the transmission of motion, we can connect driver and driven by clutch. Okay, whereas brakes are used to stop the moving member or to control its speed. Okay, so let's start understand the types of brakes which we are going to learn in this chapter. Okay, so first brake are classified in three categories. First is hydraulic brakes, second is electrical brakes, and third is mechanical brakes. So in our syllabus there are we are going to study the mechanical brakes according to the direction of acting forces. As you know that if the direction of force is maybe radial or maybe axial, and based on that radial brakes are there and axial brakes are there. Okay, which is classified according to the direction of force and with respect to axis of the drum. Okay, so first we are going to study the single block brake or single shoe brake. So before starting that, first of all we have to understand what is the arrangement in this type of shoe brake. Let's check this. So as you can see, L type lever is there which is connected to O, which is a pivot point, and we apply the force P at the end of that lever. Okay, and you can see the shoe or block is at the center and which is connected to wheel. Okay, which is connected to wheel, and when we apply the P force, this shoe is forced against the wheel and there is a frictional force will be generated, and due to that the RPM of our element will be decreased or we can stop by applying the P force. Okay, as you can see, when we apply the P force, what will happen? The reaction force due to this force of the shoe, the reaction force will be there at a surface contact, and due to that friction force will be that, which is you can see Ft. Okay, and okay, Ft is a tangential friction force. Now there are three types of arrangement we can see in this single shoe brake. You can see on a screen right now the friction force Ft and pivot point O. This arrangement can be different. Let's see in a screen. You can see that the O point is right now below the friction force, but this pivot point can be in a line of friction force, and also this pivot point can be above the friction force. This type of three case we will study in this chapter. So first we start with a single shoe brake, that in case number 1 you can see that the frictional force is in a line of pivot point. Okay, so it is very basic and very simplest arrangement is there. You can see the P is a force at the end of lever, reaction force at a point of contact, frictional force which is a tangent to the wheel, and pivot point O. Length of this lever is a L, and from pivot point to the reaction force distance is a X. Let's take the terminology. P is a force applied at the end of the lever. Okay, now next is a reaction force pressing the brake block against the wheel, and R is a radius of the wheel. Okay, 2 theta. 2 theta is the angle of contact, means we applied the shoe which is in a shape of arc, and this arc of contact we can consider as an angle of contact, which is a 2 theta. Okay, remember that angle which making that surface is a 2 theta. Okay, then the mu coefficient of friction and the Ft, tangential braking force. Okay, now let's understand. As you know that frictional force F is equal to mu into Rn, mu is equal to coefficient of friction and Rn is equal to reaction force. Okay, so what will be the braking force here? As you know that any rotary element, if you want to rotate that element, you have to give some torque. Right now we want to decrease or stop that rotary motion. So we have to apply some braking torque. And what is a torque? Torque is equal to force into distance. Which distance? Means radius of the wheel. And which force? We apply the friction force here. Okay, so friction force. So our as a friction force you can write here mu into Rn. So braking torque Tb is equal to, you can write here mu Rn into R. Okay, now we are going to taking the moment. Okay, let's take the moment. And as you know that what is the moment? Moment is equal to force into distance. So for this whole system, let's take the moment. So you can see there are three forces is there. First is a P force we have applied, reaction force Rn, which is a perpendicular to point of contact, and third is a Ft, which is a tangential friction force. Okay, let's take the moment. First is a P force into L distance and Rn into X distance, and Ft we are not considering the Ft right now, because Ft into distance means Ft into distance is equal to 0 right now, because Ft is a passing through the O point. Okay, so our equation will be Rn into X is equal to P into L, making the Rn as a subject. Rn is equal to P into L by X. Now the value of Rn as a equation number 2, we will put that in equation number 1. So our braking torque, so as you know that braking torque is equal to mu into Rn into R, small r. Now we will put the value of Rn, which is the P into L into by X. So our braking torque will become mu into PL into R by X. Okay. Okay, this is the first case we have taken, but right now we have considered the rotary motion of wheel in a clockwise direction, but it can be rotate in a anti-clockwise direction, but our formula will be same for particular case number 1 only, because as you can see, friction is equal to mu into Rn, braking torque is equal to frictional force into radius, and frictional force is equal to mu into Rn we will put in equation number 1. So finally we will find the braking torque. Okay, and we will take the moment. Now check this. When we take the moment, P into L and Rn into X, which will be the same as the last when the rotation in a clockwise direction, and we will find the same formula here. So remember that when the pivot point is in a line of action of the frictional force, in both case means in a rotary means in a both direction, clockwise or anti-clockwise, our equation braking torque is equal to same. Tb is equal to mu into PL into R by X. Okay. Now let's take the case number 2. In a case number 2, as you can see here, what is the change? You can see the pivot point is above the frictional force. Okay, you can check the Ft, line of Ft and line of which is passing through the pivot point O is as a distance is given as a. Change will, we have to consider that distance, and we have to consider the frictional force when we take the moment. So let's take the moment. Okay, and in moment we have to consider Ft right now, because there is a distance between Ft and O is a. Okay, so moment, check this, Ft, which is the direction, you can see the direction, and Ft with respect to O is in a anti-clockwise direction, and you can say Rn is also in an anti-clockwise direction with respect to O. So these both will be in a left side, and force P with respect to O is in a clockwise direction, so we will put that in a right side. So Rn into X plus Ft into A is equal to P into L. Now as you know that frictional force Ft is equal to mu into Rn, so we will put that value here, and you will see that Ft is equal to mu into Rn. Now we will make the Rn as a subject, P into L divided by X plus mu A. Okay, and value of this Rn we will put in a braking torque, which is equal to mu into Rn into small r. So the final equation will become, you can see here, braking torque is equal to mu into PL into R divided by X plus mu A. Okay, but now let's assume that wheel is rotating in a anti-clockwise direction. What will change? You can see the Ft, the direction of friction force will be inversely, and now you can see Ft will be in this direction. So minor change will be there in a derivation. The frictional force, when we take the frictional moment of frictional force, it will be change the position and it will be in a right side. You can see the Rn into X is in a anti-clockwise with respect to pivot point, whereas the P force and the frictional force will be clockwise with respect to pivot point. So you can see here the final Rn is equal to PL upon X minus mu. You can see this. What will happen? Our formula will be changed. You can see the braking torque is equal to mu PLR divided by X minus mu A. So there is a minor change, is a plus and minus whenever the rotation of wheel is changed. Okay. So now we will take the case number 3. In case number 3, you can see on a screen what will happen. The frictional force is above the pivot point. Check the figure. You can see on a screen there is a distance A is given between the frictional force Ft and pivot point O. Okay. So what will be the change here? Minor change will be there in considering the moment of Ft. Let's see. The P force is in a clockwise direction with respect to O. Rn is anti-clockwise with respect to O. These two forces are fixed. But Ft, check this. Right now Ft is above O, and rotation of that moment with respect to O will be in a clockwise direction. So what will happen? Rn into X is equal to PL in P into L plus Ft into A. But Ft is equal to mu into Rn, you can put there, and you will make the subject Rn here, Rn into X minus mu A is equal to PL. So Rn is equal to PL divided by X minus mu A. Okay. So final braking torque is equal to mu PL into small r divided by X minus mu A. Remember that this case number 3 in which Ft, frictional force, is above the pivot point. But there is also second criteria we can take this. Wheel is rotating in an anti-clockwise. So Ft will be changed. Ft, direction of Ft will be changed. And when we take the moment, you can see this Rn into X plus Ft into A is equal to PL. Now put the value of Ft, which is equal to mu into Rn, and our final formula will be braking torque is equal to mu into PL into R divided by X plus mu A. You can see what is the change between them. There is a minor change, is that plus and minus. And during example, we have to take the moment again, and according to assembly or according to the arrangement, we will decide there will be plus or minus. Okay. Thank you.